Hello and welcome to lesson 1 of chapter 9, Differential Equations. Today we're going to look at what is a differential equation and how can we use a given equation to see if it satisfies a given differential equation. Lesson 2 will be something called slope fields, and lesson 3 we will be solving differential equations more intensely. So a differential equation is an equation involving one or more derivatives of an unknown function. In this section, we will denote the unknown function by y equals f of x unless the differential equation arises from an applied problem involving time, in which case we will denote it by f of t. So here are some different examples. So this very first one, we have dy dx on the left-hand side. That would be our f prime or y prime, and 3y on the right-hand side. This is a differential equation of order 1 because we only have a first derivative. On the next line, we see that we have a second derivative indicated by this front term here, d squared y over dx squared, minus 6 dy dx plus 8y equals 0. This is a differential equation that has a second derivative and a first derivative and the function y itself. This would be a differential equation of order 2 because the highest derivative is the second derivative. The next one, much more complicated equation here, we have d cubed y over dx cubed minus t dy dx plus t squared minus 1 times y equals e to the power of t. This one would be of order 3 because the highest derivative we have is a third derivative. So I want you to pause for a second and see if you can figure out what order the next two would be and come back when you're done. All right, so hopefully you are back from taking a look at the last two examples and see if you could figure out what order these would be. The first one should be order 1 because the highest derivative is y prime, first derivative. And the next one should be order 2 because the highest derivative is y double prime, a second derivative. So we say a function y equals f of x is a solution of a differential equation on a given interval if the equation is satisfied for every x in that interval when y and its derivatives are substituted into the equation. So all these ones we saw, if we were given some equation y, it is only considered a solution if you can plug it into the equation along with its derivatives, depending on which of these you're in, dy dx, possibly a second derivative or a third derivative as well, and it actually works out in your equation. So for example, y equals e to the power of 2x is a solution of the differential equation dy dx minus y equals e to the 2x. Or in other words, y prime minus y equals e to the 2x. It doesn't matter if we use dy dx or y prime here. Okay? It is more common in a differential equation that you will be using dy dx. So if we check and see if this is true, on the interval negative infinity to infinity, so for all real numbers, if we substitute y and its derivative into the left-hand side of this equation, we should get the right-hand side. So first, let us find dy dx so that we can substitute it in. If we find the derivative of this equation, we should get 2e to the 2x. So a reminder, we need chain rule here. The derivative of e to the 2x is e to the 2x times the derivative of the exponent, which is 2. So we get 2e to the 2x. So if I try and substitute in here, dy dx was 2e to the 2x minus y, which was e to the 2x. And we're trying to figure out if this equals the right-hand side. If I actually subtract these two things here, I actually do this subtraction, 2e to the 2x minus e to the 2x gives us 1e to the 2x, which is in fact what the right-hand side equaled. And therefore, this equation, y equals e to the 2x, is a solution of the given differential equation. This is not the only solution. So for example, let's say y was equal to some c times e to the 2x, where c is a constant, plus e to the 2x. We're being told that this is also a solution for every real value of the constant c. And so let's try. If we do dy dx, we're going to get c e to the 2x, or sorry, e to the x, not e to the 2x, c e to the x plus 2e to the 2x. That would be our derivative of our function y. If we try plugging that in, we had dy dx minus y is supposed to equal e to the 2x. dy dx here was c e to the 2x plus 2e to the 2x minus y. Y is c e to the x plus e to the 2x, and this should equal e to the 2x. So we've plugged dy dx and y into the left-hand side. When we do that, I realize I've made a mistake here. Again, I've put e to the 2x in my exponent. I should just have e to the x in my derivative here, this one. So when I do that, I get c e to the x plus 2e to the 2x minus c e to the x minus e to the 2x equals e to the 2x. And you'll see that your c e to the x's cancel out. And we end up with 2e to the 2x minus e to the 2x, which gives us e to the 2x, which is in fact the right-hand side. And therefore, this equation, y equals ce to the x plus e to the 2x, is also a solution of this differential equation for every real number and for every real value of the constant c. So the next question is asking us to find the equation for the differential equation. This should say find the solution for the differential equation, the same one we were just dealing with a given initial condition. So we in the previous page were told that any y equals c e to the x plus e to the 2x is a solution of the differential equation dy dx minus y equals e to the 2x. So we're just being given some additional information in terms of this initial condition. So basically you're being given an x value and you're being given a y value. You need to plug it into this general form of a solution to actually figure a particular solution to this differential equation. So y would be 3. We don't know c, that's what we're going to be trying to find. We have e to the 0 plus e to the power of 2 times 0. So you get 3 equals c plus 1. So therefore c equals 2. Oops. And therefore a solution to the differential equation with this initial condition is y equals 2e to the x plus e to the 2x. If we had been given a different initial condition, we would have a different solution. So we sometimes call this the particular solution that satisfies the initial condition given. A new differential equation here. Confirm that this equation is a solution of the initial value problem of y prime equals x squared y, and this is my initial condition. Okay? So we want to make sure that this solution satisfies this differential equation given to us here. So in order to figure that out, we first need y prime. Y prime would be 2e to the x cubed over 3 times 3x squared over 3. Again, chain rule is needed when you do the derivative of this, which gives us, those 3's cancel out, 2x squared e to the x cubed over 3 is my y prime. So we're trying to make sure that this actually works in our differential equation. Usually when we're trying to confirm if something is a solution, we're trying to find y, okay, to find the solution. So if we have this y prime and we plug it in for y prime in our differential equation, we would get 2x squared e to the x cubed over 3 equals x squared y. And we know that there could also be a constant in your y prime if you're doing an antiderivative, right? So then we can move our x squared over and we get 2e to the x cubed over 3 equals y. Now this was not the y that we were given. The y that we were given has a constant, but we know that if we went from this y to this y prime, problem is that we would be able to possibly have a constant here and we would get the same y prime value. So if we have 2e to the x cubed over 3 plus some constant equals y, and we plug our initial condition in, we would get 2e to the 0 over 3 plus c equals 3, or 2 plus c equals 3, or c equals 1, which would give us 2e to the x cubed over 3 plus 1 equals y, which was, in fact, the equation we started with. That is how we can figure out if this initial condition is the exact initial condition we need. Usually we are given some maybe additional information, like we might be given just a y prime and be told to find the y. We wouldn't be given the y to start, find the y prime, then plug the y prime in. Maybe just given straight up, given a y prime and being told to find the solution given this initial condition. So you would have your y prime in, you'd find your y, plug in your initial condition, and then find your final y with that initial condition taken into consideration. Because we were given y here, we could have also just plugged y in on this side and worked our way out and made sure that the two sides were equal. However, if we do that, we do need to make sure that we include this plus c here, because if we take the derivative of y to get down to y prime, we have to remember that you could have a constant that is in play. If we just plug this y directly in here, we're not going to get that the two sides are equal. We're missing the plus 1 on the left-hand side. Okay? So we do need to make sure that we consider that this c exists. Next one, for what values of r does this function satisfy the differential equation given? So we see we have a y prime and a y double prime in this differential equation. So we're going to need to figure out what y prime and y double prime are, plug them in, and figure out what r would have to be to make this all work. So y prime would be e to the rt times r, or re to the rt. Y double prime would be re to the rt times r, or r squared e to the rt. We plug that into our differential equation. Our differential equation is y double prime plus y prime minus 6y equals 0. Y double prime was r squared e to the rt. Well, y prime was re to the rt, and y is e to the rt. Hopefully we'll notice that there's an e to the rt in everything. We can factor an e to the rt out. Then we end up with a quadratic. We can factor that. And then we can solve for the quadratic. So we get r equals -3 or 2. We don't get any conditions from this because remember, e to the rt, that's never going to equal 0. So we get r is equal to -2, or sorry, -3 or +2. And those are our values of r that we could put into this y so that it would satisfy this differential equation. Okay. All right, last one. We're going to match the following equations with the differential equations. So which of these equations could we plug into these differential equations so that they would actually work out? So each of these have a y double prime and a y prime in them. So we might want to go through and find y double prime and y prime for each of these. I'm just going to work my way from the top down. So I'm going to do number 1 first and see which works. And then do number 2, and then number 3 would have to work with the remaining one. So if I start with equation 1, we have y equals e to the x plus 7x. Y prime is going to be e to the x plus 7. And y double prime is going to be e to the x. So if I plug each of these into each of a, b, and c, which differential equation does it work for? So if I try it in a, I get e to the x plus e to the x plus 7. It's supposed to equal 0. It does not. We can tell by looking at it. That's going to give you 2e to the x plus 7. That is not 0. Okay, try it in b. We get y double prime, which is e to the x, minus 2y prime, so 2e to the x plus 7, plus 2y, 2e to the x plus 7x. This is supposed to equal 0. Well, I'm going to get some things that cancel out, but not enough. So if I expand all my brackets, again, we can tell by looking at it, we have this constant and this 14x. Those aren't going to go anywhere. 2e to the x's are going to cancel out, but I'm still going to end up with an e to the x. That also does not equal 0. So let's try C just to make sure that this one does work and we haven't made some sort of mistake finding our derivatives. We've got y double prime, which is e to the x, times 1 minus x, plus y prime, which is e to the x plus 7, times x, minus y is e to the x plus 7x equals 0. So we'll get e to the x minus x e to the x if we expand the brackets, plus x e to the x plus 7x if we expand the brackets, minus e to the x minus 7x if we expand the brackets. This should equal 0. And if we take a look, we get x e to the x's cancel out. We get 7x and 7x cancel out. And we get e to the x and e to the x cancel out. So this, in fact, does equal 0. And therefore, number 1 matches with letter C. So we'll do number 2. If you want, you can pause, try number 2 on your own, and then scroll ahead to the answer in the video, or you can walk it through with me. So we have y equals e to the x cosine x. We're going to need product rule here. Y prime is going to be e to the x cosine x, because the derivative of e is e, minus e to the x sine x. Y double prime is going to be e to the x cosine x minus e to the x sine x, if we do the derivative of e to the x cosine x, minus e to the x sine x plus e to the x cosine x. If we fix this all up, the e to the x cosine x and e to the x cosine x are going to end up canceling out because we are going to subtract there. And we're going to end up with y double prime equals negative 2e to the x sine x. So we already matched C. We don't need to try C. We could if we really want to double check our work, but really we need to try A and B. So if we try differential equation A, we can't see that anymore, but it was y double prime plus y equals 0. That was the differential equation for A. So if we try this, we get negative 2e to the x sine x is our y prime, plus e to the x cosine x is our y. It's supposed to equal 0. That does not equal 0. Nothing cancels out there. Letter B was y double prime minus 2y prime plus 2y equals 0. Y double prime is negative 2e to the x sine x minus 2y prime is e to the x cosine x minus e to the x sine x plus 2y is 2e to the x cosine x. This is supposed to equal 0. Even though we've already matched C and we ruled out A, we're still going to check here, because what if we made a mistake when we did the work up to the top left here with all of our y primes and y double primes? If it doesn't match anything, then it's probably something we've done earlier. So we get -2 e to the x sine x minus 2 e to the x cosine x plus 2 e to the x sine x, if we expand these middle brackets here, plus 2 e to the x cosine x equals 0. And hopefully we can notice that the 2e to the x sine x cancels out with the other 2 to the x sine x. The 2e to the x cosine x cancels out with the 2e to the x cosine x. That, in fact, does work. So therefore, number 2 matches with B. So number 3 must match with A. If you want, you can go through and actually verify that. Right? So if you actually wanted to go through and find for number 3, the first derivative, second derivative, and then plug in y double prime and y and make sure that A works, you could do that. And that might be a good exercise on your own to just make sure that that works. Plugging it in, it should work. If it doesn't work, something has gone wrong with your y double prime or your y prime there. And that's it for this section.